is also interesting as far as R290 is concerned, particularly the low temperature cabinets, and that is the operating envelope. So what you can see here on the graph on the right side is the operating envelope for R290 compared to more conventional refrigerants such as 22 or 10AR32, and the same applies to 4A and some others. And generally, because R290 has a low discharge temperature, it also has a relatively flat saturation temperature curve. So the pressure ratio is generally, or compression ratio, is generally lower compared to other refrigerants. But the operating envelope is wider, so you can have better performance over a wider range of conditions. Perhaps the most important aspect related to the circuit design is the design of and selection of heat exchangers. And of course, all refrigerants have got different thermophysical properties, and the idea is to try to optimize the design of the heat exchanger to take advantage of those thermophysical properties of the refrigerant. And if this is done in an intelligent way, you can actually reduce the refrigerant charge quite substantially and improve the system performance, both in terms of cooling capacity if necessary and operating temperature differences. A lot of products now use obviously thin tube evaporators and condensers, but often with a lower, smaller tube diameter, 7, 6, 5, even 4 millimeter, 4.25 millimeter diameter tubes. The advantage with this is that you are greatly reducing the circulating refrigerant charge in the system. Of course, microchannel heat exchangers are also used particularly on the condenser. I know particularly for commercial refrigeration, this can be a sort of personal or subjective choice because particularly in some environments, these types of heat exchangers are known to become quite clogged up. But the technology is evolving, and in fact, today you can get microchannel evaporators, which have been designed to handle a little bit of frosting and the defrost water. So it's worthwhile to investigate these technologies because at the end of the day, it's not only reducing the charge, but they also contribute to beneficial cost reductions. Less copper, less aluminium, and less refrigerant as well. So it all adds up in the long run. Just to give an example, even just maintaining the same tube diameter, by designing the condenser circuitry, significant improvements can also be gained. Of course, when you switch from a larger diameter tube to a smaller tube, there is a requirement, there is a demand to redesign the circuitry to deal with the possible increased pressure drop. But what you can see here in this graph on the right side, this is simulations arising from the different circuitry designs on the left, and you can see quite significant reductions in system charge, operating charge, reducing by almost a half, or halving the charge, yet with equal increased performance. So it is a beneficial exercise to go through. Lastly, in terms of general charge optimization, at other components. We mentioned the compressor earlier. Particularly, it's worthwhile mentioning that if the correct oil, or some compressors use better oils than others, if the oil is low solubility, then you can reduce the refrigerant charge in it by up to half. Reducing the charge in the evaporating condenser, as we mentioned before. And if you carry out an exercise and determine the refrigerant charge in each system component, it can also give you a bit more of a focus in terms of where you should apply your efforts to reduce the refrigerant charge further. Okay, moving on to the safety aspects in more detail. Once we've obviously reduced our refrigerant charge as much as possible, there's a number of sort of mitigation measures that we can introduce into the design of the equipment. One approach which some manufacturers implement, which incidentally we didn't apply in the current system that we're talking about, it's leak detection and some form of mitigation. So, for instance, you may choose a leak detection method that can be gas detection, although the reliability can be not so good. However, we can also look at using system parameters, for example, temperature measurements and pressure measurements, and use that to infer whether there's a refrigerant leak or not. Or indeed, looking at ultrasonic sensors that listen to the sound of the leak. And when we're confident that a leak has begun, the controller initiates the mitigation action. And in the image here, we have an air conditioner, but it's initiating airflow, so the airflow is used to disperse any refrigerant leak that occurs around the equipment, or indeed it can be shut-off valves that limit the quantity of refrigerant that is leaked from a given part of the system. As I say, we didn't select this option for the display cabinet because actually the level of risk was already extremely low. But in some types of equipment, it can offer a significant benefit. Another important aspect is improving leak tightness or reducing system leakage. And I guess you all know that, it's pretty obvious. If you can apply as many measures as possible to minimize leakage, then actually overall it will reduce the, if you do get a leak, it will likely result in smaller leak holes. Smaller leak holes cause or result in smaller refrigerant mass flow rates and lower concentrations. And of course, there's broader benefits from having improved leak tightness, mainly the reliability of the equipment, best performance over the lifetime, and of course, reducing environmental impact. So sometimes it requires a bit of effort, but overall there's huge benefits from redesigning systems, components, fittings to reduce leakage. Of course, the classic approaches to avoid all flare joints, flare connections. I don't even need to say that. There's an ISO standard, ISO 14903, which is specifically on component tightness for refrigeration systems. Ideally, all components should comply with that. Then, of course, there's pressure and tightness tests that are applied to the system that are prescribed in the given safety standards. There's additional checks that can be applied, so for example, mechanical impact tests, vibration tests, resonance, on-off cycling, drop tests, even if it's a movable cabinet, corrosion tests, and long-term run tests. So there's a whole variety of rigorous assessments that the manufacturer can carry out on the cabinet in order to demonstrate and to determine how to reduce the leakage. Okay. The next stage is sort of more directly related to the flammability of the refrigerants. It's called it depends which standard you look at, but zoning is a zoning exercise or leak simulation test. And this is the logic behind it. So if you install your R290 or any other flammable refrigerant cabinet in a shop, and it's surrounded by other equipment that is not designed to handle flammable refrigerants, but then there is a possibility, or a very small possibility, that a leak of refrigerant from the, say, R290 cabinet could migrate to one of the adjacent cabinets, and that mixture of leaked refrigerant and air could be ignited by, for example, electrical components. And of course, it's not only the electrical components within the adjacent cabinets, there may also be other ignition sources around the supermarket or the shop. So, for example, floor cleaners or vacuum cleaners, somebody said steel-tipped high-heel shoes. I don't know whether those are potential sources of ignition or whether they're worn very often, but in theory it could be. So the idea is to ensure that if there's a leak of refrigerant from that cabinet, it does not form a flammable mixture or potentially flammable mixture at any point around beyond the boundary of that cabinet. But for this, there is a test. So the various standards describe what I call a surrounding concentration test, and it's something like this. So we have the cabinet here on the left. The red dots are gas sensors. So they are surrounding the cabinet itself, both at high level, with refrigerant containing parts on top, and of course, floor level. The arrows here are indicating potential leak points. So there's a condenser unit on the top here, and condenser, I should say, it's a fine word. So we simulate a leak from what's known as the critical leak point. So maybe a pipe at this end of the condenser, that end of the condenser, the filter dryer, or wherever. You choose the point that results in the highest concentration. Also within the cabinet itself, so for example, with the return ends with the evaporator. In this particular case here, where we have glass doors, the choice of leak points within the cabinet is not so important, because what happens is the refrigerant leaks out, the fans are operating, and they mix the refrigerants around the insides of the cabinets. So it's not so important. On the right-hand side here, we can see the view from the technician side. So we have the refrigerant cylinder here on the electrical balance, manifold gauges as the tube is going into the cabinet, where there is an orifice of a certain size to provide something close to choked blow sonic velocity leak. The room needs to be of a specific size, and there must be no airflow, air movement, and so forth within the space. So the space must be relatively airtight, so the leak refrigerant doesn't migrate out and influence the results. So here are some results of the measurements. This graph here shows concentrations arising from zones and different locations that are measured at different levels of concentration, and then the leak ends once the refrigerant charge has been exhausted and the concentration diminishes. Within the Colombian standards, the NTC, the boundary for the maximum allowable concentration is around 90%. In the international standards that we developed, actually a few years after the Colombian standard, the boundary was around 50%. I should say these little peaks here are probably not much to worry about. Actually, the type of gas sensors that we used on these tests are quite sensitive, and they've got a very short response time. If you use other types of sensors with a slower response time and a diffusive type sensor rather than an aspirated sensor, you get much smoother or average distributions that you see here. The next test here is, let's say, a more challenging test, and this is basically a door opening test. So you leak the refrigerant from the evaporator, and then once the leak has finished, you open the door remotely with a piece of string or rope. You open the door and you look to see what concentration develops in front of the cabinet. Because when you open the door, you have a big chunk of potentially flammable mixture that falls out in front of the cabinet. And actually, this eventuality cannot be eliminated. And in fact, it happens with domestic refrigerators. If you have a leak inside the domestic refrigerator, you open the door, you will create a flammable mixture outside the front of the cabinet, albeit only momentarily for a few moments, but it will be quite green. And so you can see you get a peak above the LFL here. It's just for a minute or two, but this is tolerated by the safety standard. Okay, everyone's telling me I don't have much time left, so I'll try to hurry up. As part of this process, we use CFD, or computational fluid dynamics, to understand the distribution of refrigerants with a local leak. We do some simulations. You can see this example here where the refrigerant is leaking into the cabinet itself. See, over a few minutes' time, over a few moments, the cabinet fills with the mixture. The red colour means is okay. Flammable is green and red, so it fills with refrigerant. Some leaks out, and you can see the results. Then, the next one is where the door is opened, and you can see the process of what happens when the door is opened. So this flammable mixture briefly forms, but then it disperses quite rapidly. Another example here is where we have a leak from the condenser. You can see mixture spreading around a little bit, but it also disperses quite rapidly. And in this case, we very seldom reach flammable concentration. And then the last case is where the condenser fan is on. Here is that's another video, but you can see the size of the mixture, the extent of the mixture is very, very limited. After the zoning phase, we want to look at the potential sources of ignition and eliminate those from the cabinet. This is quite an important factor. So we systematically look through all these different potential elements. So we've got the compressor here, there's electrical, but there's no sources of ignition. Evaporator fans, they're also electrical, but they don't spark. Lighting is also okay, condenser fans are okay. The only item here that has potential sources of ignition is the electrical box, which contains contactors, relays, and so forth. And so actually, whilst we're doing the leak simulation test, we also consider this. So we put a sensor in there to ensure that when there's a leak of refrigerant, we don't reach more than, say, 50% of the LFL. And in fact, in the design here, you can see a small sort of boundary wall fitted here, which ensures that no refrigerant approaches the electrical panel there. Alternatively, you can use EX type components, but then there's a significant cost detriment to that. We have a risk assessment procedure following this, so we look at the likelihood of leak of refrigerants, then some ignition sources, the dispersion of the mixture. If it's a quantitative risk assessment, we use probability calculations, and then we try to model or simulate the severity and consequence if we do get ignition, whether there's a fire or explosion, and so forth. As we quantify these and say, well, is it severe or is it not? But of course, in this situation, this cabinet, the risk is extremely low. Then the last step really is compliance with the applicable safety standards. So in this, for this case, we looked at the IEC 60335-2-89 and in parallel the NTC 6228, the Colombian national standard. And this more or less covers a lot of the subjects that I talked about earlier. It basically provides a checklist. And the last element really is the marking. So you obviously need to provide a manual, instructions, and the appropriate marking and signs to go onto the product. There were some field trials which Edwin mentioned a little earlier, and so far those seem to be very favourable. I believe Edwin can talk about those in more detail. And that's it. Just a few final remarks. I probably don't need to say it, but overall there's a significant environmental benefit from using R290. That's why we bother with all of this trouble. The TUI is reduced by at least a third. It depends on the national electricity carbon emissions for the electricity supply, but obviously you eliminate the emissions associated with refrigerant leakage. Cost benefits can be realised, so lower refrigerant costs, less copper, possibly less aluminium. Safety-related costs can be negligible. There's a refinement process like everything else. At the moment, R290 compressors or some types of compressors have a cost premium, but of course, by the time everybody uses R290, there should be no impact on the cost. The mass of materials in an R290 compressor is identical to an R404A or R410A or an R22 compressor. There should be no difference in cost. Just the cost of a thin yellow sticker, right, which is obviously nothing. At least at this stage, as the technology evolves, it's really important to involve thorough flammability risk assessments and any necessary testing. For the first few designs, it's very sensible. At least as a manufacturer or producer, you get to obtain a good feel and understanding of the flammability hazards. And last point, today there's many large R290 cabinets being used, particularly in Europe. They're now being produced in North America and Asia as well, Australia, and I'd say at least in Europe, it's almost business as usual, common practice. My supermarket down the road, they have aisles and aisles of R290 cabinets, actually with more than 400 grams, with up to 1 kilogram in these cabinets. It's standards in most supermarkets now today. So, muchas gracias. I hope it was interesting to you, and I'd be very happy to answer any questions. Thank you. Let's see if there are questions from the group. No, I don't think there are any questions. Again, no questions?
No question.
Pascal, your translation must have been excellent.
Thank you.
Yes, it was thanks to the translation. It seems so.
Luego, Edwin.
¿La van a pausar?
Okay, you want finished?
Yeah, Daniel.